All right, so we're going to have 14.6, a second day here, really focusing in on how the gradient can help us. The gradient, of course, is a vector. We saw that yesterday, whose components were all the partial derivatives of a function with respect to x, y, and even perhaps z if it is a three-dimensional vector. But let's just take a look at a few other properties of the directional derivative first. Notice that this subscript, it might be a little hard to see. What if we had the derivative in the direction of opposite of u? And of course, the directional derivative we learned yesterday is the gradient dot producted to a unit vector. So what if our unit vector is actually the opposite of u? Well, we saw that with cross products and dot products, if there's a coefficient out in front, we can actually move it out in front of the whole multiplication. And what we're going to see then is, very quickly, that that negative is out in front of gradient of f dot u. So it's really the opposite of the directional derivative in the direction of u. Maybe that's not a big surprise. Also, we'd have the directional derivative with respect to I. What would the gradient dot I be? Well, all other components would be multiplied to 0, so we just have f sub x. That is the partial derivative of f with respect to x. Likewise with j, the gradient of f dotted to j is just f sub y, and then gradient dotted to k is f sub z. So, what are we really seeing from this information? F sub x is the derivative of f in the I direction. F sub y is the derivative of f in the j. And f sub z is the derivative of f in the k direction. Hopefully no big surprise there. Well, let's keep going here. Any direction unit vector. Wow, you know what? I wish I wouldn't have written this word normal. Let's replace it with the word perpendicular slash orthogonal. Got to fix up these notes a little bit. I'll be honest with you, a lot of math courses use the word normal to mean perpendicular. Really, we shouldn't. Especially in our text, we get more specific using the word orthogonal or perpendicular. It would be better to do that. Sorry about that. So any direction unit vector perpendicular or orthogonal to the gradient is a 0 rate of change. Now, sometimes kids look at that and they're almost like, wow, is that right? Well, let's remember the dot product. We brought this up yesterday with our proof. What's another way of looking at the dot product of A dot B? What do you think? Magnitude of A times the magnitude of B times what? The cosine of the angle between them. And we're saying actually that our vectors are perpendicular, that they're pi over 2 radians apart. And a unit vector always has a length of 1. So real quickly, guys, what we know is that the gradient of f dotted with a unit vector u is going to be the length of the gradient vector times the length of u, which is 1, times the cosine of theta. So, of course, what we're seeing is the cosine of pi over 2 is 0. So every time a unit vector is perpendicular to the gradient vector, the rate of change of that function in that direction is 0. Our z value would remain the same. It's not changing the height of it if we're in a 3D type of a graph. So those are just a few, loose ends to maybe tie up. And let's press on to something really, really cool. We're going to do a quasi-proof here. And what we're going to investigate is, suppose we have a surface. That's a sum surface. It could be a quadric surface. Perhaps it even is a level surface of a function of 3 variables. In fact, that's really the way we want to look at this. Ordinarily, if I gave you f of x comma y comma z, that function value, we could say the w value, we couldn't even graph it. We couldn't graph it. That would be going in to a fourth dimension. But we could look at level curves. We could say, let's say that k is some constant. Let k be set equal to our function. And then this picture right here on the screen could represent a level curve. Let's say that there is a point, x naught, y naught, z naught, call that point P, on this surface. And let C be any curve that lies on that surface and passes through P. So my goodness, we're not getting real particular here. We're not getting real picky. We're saying, look, here's a surface. It's really a level curve. There's a point on it. Pick any curve that goes through point P. And now we've got to recall from last unit, recall from that last chapter, that if you have a curve in 3D, we could represent it as a continuous vector function. So we're saying, hey, for that curve C, we've got a vector component of x of t, y of t, and z of t. And while we did that a lot, I still have this hanger up here where we were talking about tangent vectors and so forth, right? So we've got our r of t vector function describing that curve. Wow, and talking about that vector, where you've got r prime, the tangent vector. Wow, that's linking in right here. But let's just say that we have t sub 0 correspond to P. So we let t sub 0, the initial t value, correspond to x naught, y naught, z naught, to point P. So here's what we're saying. Since C lies on that curve, since the curve lies on that surface, I should say, this vector-defined curve must satisfy the equation of S. So every point on C, which I've highlighted, would make our level curve equation true. So, hey, how about I just plug in the coordinates via the vector function? I could say x of t, y of t, z of t, plug that into our function. And that would have to be true. Well, then what? Let's take our derivative with respect to time, with respect to t. And you could draw yourself a little diagram off to the side if you'd like. You could say, wow, f is here. It's a function of x, y, and z. But all of these variables are functions of t. So I'm going to take my derivative with respect to t. Let's review the chain rule. Help me out. What do we get? Partial derivative of f with respect to x. Chain rule times what? dx dt. Take our derivative with respect to y. Chain rule, dy dt. Take our derivative with respect to z. Well, then we have dz dt. Oh, look at that. That's nice. Then all of a sudden, kids will say, well, the derivative of the right side, what's that? 0. Now, I hope right now this looks oddly familiar. At first glance, you look at this, you'd say, hey, Mr. Dobner, it's just the chain rule. We've done that so many times. But did you know, surprise, 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 that this is really a dot product of two vectors? All of a sudden, kids are like, whoa, wait a minute, is that right? Well, let's check it out. The gradient of f, we could say, well, it's f sub x, comma f sub y, comma f sub z. And here's my function r of t. Help me take a derivative of it. Wouldn't that just be dx dt, dy dt, dz dt? Well, son of a gun, would you look at that? You could dot product those two together, and you get this equation that we just came up from the chain rule. Unbelievable. Unbelievable. Wait a minute. Hold on a second. Now for the ultimate, now we're going to look at this and say, hold on a second. Dot products equaling 0. We're going back 2 chapters now. When your dot product of 2 vectors equals 0, that means that your 2 vectors are what? Orthogonal. Wow. So therefore, gradient of f and r prime of t are orthogonal, or if you'd rather, perpendicular. The words mean exactly the same thing. Wow. Well, wait a minute. We know where r prime of t is going. Look at this picture. This picture, you've got r prime of t right here. You could say, well, that's a tangent vector. It's not the unit tangent vector. You know, we'd have to divide by its length to get that. But it's certainly a tangent vector, isn't it? And then you'd say, well, wait a minute. I've got to be perpendicular here. My goodness, the gradient is going to be perpendicular to that. Holy cow. Wow. That has a lot to say with this. Tell you what, let's go over to the other side. Remember from 2 chapters ago that if you wanted to write the equation of a plane, let me bring that back. The equation of a plane, I'll even draw you a nice little picture here, and you'd say, here's a nice little point. We'd say x naught, y naught, z naught. You need a point on the plane. What else do you need? A vector that's perpendicular to it. A vector that's perpendicular. Can you think of a vector that's perpendicular to it? Hint, hint, hint. The gradient. Now, immediately kids might go, wait a minute, Mr. Dobner, the gradient is just going to be the vector that's perpendicular to r prime of t. But r prime of t is going to be a tangent plane where actually all the directional derivatives, vectors, or direction vectors at least, are going to be contained in there. So holy cow, what were we doing before? We'd say, look at this perpendicular vector of a comma b comma c. A little while ago we'd write this out. We'd say, don't you take the dot product and then you just get 0. You bet. Holy cow, look what we have here. This is unbelievable. What you're seeing is you take the gradient vector and you have an incredible way to write this tangent plane. A tangent plane that can be used to approximate a surface, of course. And unbelievably so. Look at that. All of a sudden, everything is set up so nicely. Oh, I lost our video. Well, technical difficulties. I'm going to have to go back and watch this video and make sure there isn't a huge gap. Sorry, I must have pressed the wrong button or something, but hopefully we can see what's happening here. The gradient, that is, all these partial derivatives at an initial point, are going to be our vector that will be perpendicular to a tangent plane. My goodness. And that is fantastic news. It's going to allow us to write an equation of a tangent plane incredibly quickly, very simply. And here we go again, this ongoing theme of this unit. We're going to need directional derivatives. Yeah, you want to memorize that. And then the normal line. Well, my goodness, let's have a real quick review of 2 chapters ago. How do we write the equation of a line in space? Well, parametrically, it was like this, wasn't it? Where we had an initial point, and we also had a direction vector. We had a direction vector on a line. So this right here is a line in 3D. And our